no introduction in Cambridge. I think Renzo is responsible for my first year a few years ago. So I'm responsible for this talk. But Renzo is going to talk this morning about the energy spectrum of magnetic knots and links. So, welcome.
Thank you very much, Rob. It's very nice to have you as chair. Okay, so this is a joint work with Francesca Maggioni, and is very much based on Keith's previous works. I'll consider a very simple approach of ideal magnetohydrodynamics, and my field B is given as a divergence-less field embedded in tubular structures that might be linked or not, and I assume that the field obeys this ideal induction equation, and these have finite energy. The energy of the field is given by this formula, and we consider magnetic relaxation under, say, standard diffeomorphisms in R3. The signature is given by the total volume of these knots and links, V, and fluxes associated with each tubular knot or link are also given here. And we assume that this stays constant, V stays constant, and fluxes stay constant during this ideal relaxation. The question of minimum energy states related to topology was addressed years back, and we have these realization by Keith that the min of the magnetic energy on dimensional grounds can be shown to depend on this function m of h, little m, where this m of h is a positive dimensionless function of the twist h present in these tubular knots and links. And because we consider phi and v constant during this relaxation, and hence we can ignore them. I'll up to a certain point I will keep track of these, and then at a certain point onwards I'll set them to 1 for simplicity. Question is, what is this m of h? You can say anything about that. So in 2001, Keith just focused on this problem, determine m min, i.e. the minimum of the function m of h at there's level of h, the twist, for knots of minimum crossing number, 3, 4, etc. Okay, so for zero-framed knots and links, we can prove that m at 0 is actually C min, and this is consistent with the clear speculations of Keith in 1990 about the relationship between m of h function and topology of the system at the relaxed state. So that m min, at least for zero-frame knots, is nicely related to C min.
What's C min?
The minimum crossing number, topological crossing number of knots and links. That's nice, but of course, question is that we may have same C min knots that might relax to a minimum energy that in principle might not be the same. And this is of course very clear when you inspect the knot table. For each topological crossing number, only from 5 on up to 4 we have just one knot type, and then knot types increase exponentially, go up to. So the question remains open. We can still interpret, indeed we did with Francesca, this relationship as an average information over the knot types within C-min family. So the question is, can we say something more specific about that, and possibly find out something about this dependence on H? So we go for a more detailed description of our flux tube and magnetic field. So we take this tubular knot as a circular cross-section. Cross-section will be kept circular throughout, and of course this is puts a constraint on the possibilities of minima we explore. So the cross-section is just pi a squared. A is the circular cross-section radius, and L is the total length. Now the new thing is that we address this problem by paying attention to the coordinate system, and we will use a coordinate system that is orthogonal. This looks familiar to you, but actually this theta r, the independent coordinate, is related to the azimuthal angle, the standard azimuthal angle, by taking into account contribution from torsion as we move along the axis of our knot, or given by S, and R is the radial distance from the axis. Magnetic field, well, for simplicity, we take this magnetic field that is functional dependence on R is given here through the poloidal and the axial, or the poloidal and toroidal contribution. And we use the standard assumption on divergence less, which gives us a nice relationship with the flux function. So we move to flux function, and we introduce fluxes. Fluxes are useful to talk about twist. So we have two fluxes. One is the toroidal flux, and the other one is the poloidal flux. So the contribution along the longitudinal and meridional cross sections. We also use a standard flux tube assumption, i.e. profile described dependence on R of the field, but we actually did it in general terms in our paper, but it doesn't matter really. The twist parameter is hence defined by the ratio of the poloidal and toroidal fluxes, and you end up with a field given by this average field plus the fluctuating field. So far, okay, but then we follow this approach by Chu and Moffat for searching the minima constrained by the assumptions I told you, in particular the circular cross-section. And so we minimize these energy expressions subject to the periodicity of the flux function psi tilde. Psi tilde is just the fluctuating contribution from flux that has, of course, net zero net contribution to the total flux. So the result is the following. So we assume V and phi constant, the circular cross-section, psi tilde independent of arc length, and L independent of internal twist. So we end up with this nice analytical expression. Still, you see here phi and V, but remember these phi and V are constants. So we can set them to 1, and then we can look for rope length and rewrite this expression in terms of rope length. And here it is. So we have rope length dependence, and because we set V and phi equal to 1, you can read out this expression as M in terms of H, little m in terms of H. Rope length is defined as the ratio of minimal, let's say, length over the maximal radius in the tight knot configuration. So this is what I just said, and we can explore a little bit this expression. Lambda, the rope length, is bound to be greater than or equal to 2 pi. The tight torus is the tightest configuration, of course unknotted, and we refer to that. And these are the curves. On purpose, I left this m of h here, but actually is plotted against lambda, so there is this dependence on rope length. for the tight torus, we can estimate the energy, of course, and then we can look for minima. So the M min is given by this simple relationship between rope length and twist, H. It's interesting because it means that if you divide rope length per twist, that is a constant. So it's an interesting condition for M min. Okay, and we then proceed to use data from the Ridge Runner, the Cantarella group, and so we looked set this equal to 0 now, H. Tight torus is given by this minimum energy configuration, and we derive this reference energy, the normalized energy, and we plot this normalized energy with respect to rope length, but now we set H equal to 0 because these are the data available so far. So the tight knot spectrum is given here. We plot the energy regardless C-min families. So these have been rearranged and just plotted against rope length. We have a linear fit, and the best fit is provided by this expression. And what is also nice to notice is that this expression here is independent to great degree of accuracy to the fact that we consider knots or links. So again, we resorted to the data provided by Ridge Runner, and the best fit for links is almost identical to the best fit for knots. That's it. Thank you very much.
Questions for Renzo?
Renzo, if you have a simple tube, no link, just one single loop, and you put in twist in it, the magnetic field, will it flip over to the figure of 8? To coil?
Probably depends on...
As elastic would.
Yeah.
We can
I can prove, it's a one-line proof. It's an interesting thing, I never wrote this. You can show... Okay, so first the answer. The answer is, depends on the amount of twist. You have to expect a kink instability. So I would it depends on the ratio between the poloidal and the toroidal field. And the competition in terms of Lorentz force, we can understand that, or at least intuitively understand that. That if poloidal field is sufficiently low, then clearly it would presumably be led entirely by the toroidal field, and so you would have probably no flip. Above a certain level of toroidal, probably you would have this writhing instability, as is called in elasticity theory. By the way, you can prove, very simple, is one little calculation. If you go in the incompressible limit, the kink instability of magnetic flux tubes is of very close in number, same order, but not only same order, very close in number to the writhing instability of elastic rods, which is to us familiar in a sense when we think of this analogy between the elastic or the bending energy and the magnetic Maxwell stresses influence. So this is quite interesting. The other thing that I didn't show, sorry, but it's easy to check. Actually, this is a question to Jason. I don't know. I simply don't know if Ridge Runner has data. You certainly can extract data on curvature.
Oh yeah.
Okay. So the curvature, because I remember Sono has this, and so you can you can use Ridge Runner data for curvature, and we did it for Sono, which is the algorithm that was used by Piotr Jaransky, and you can relate bending energy to magnetic energy, and you see that the ratio of the two If you go for relatively large crossing number, I mean just above 7, so very few knots apart, the ratio of the bending energy and magnetic energy is almost constant. We can explore, 200 knots, and for 200, 300 knots, it stays constant. The ratio is, well, it depends on the reference. You can rescale bending energy as well with respect to the tight unknot, the tight torus. You can estimate that easily and see that it's constant. So it gives insight into bending energy for systems as well.
Keith?
Well, with regard to Conrad's question, I'm sure the same applies to, for example, a trefoil knot. If you have the twist parameter h and make it large, maybe larger than, I don't know what, some critical value, say 10, then there's a tendency as h increases for the knot to expand, actually, decrease in cross-section, but expand in length. And I'm sure that will become unstable again to kink type instability. So the minimum energy configuration for large h will actually be very complicated, although still a trefoil knot, it will have lots of kinks in it.
So I would ask how the things would change if you assume that twist is set to 0. So that you have some, if you imagine some rope, that you have a constant cross section and you don't allow to twist it, so that you have only right.
Well, that we are led to look at the read runner and the data available there. There is there is a rope length information. Here is a relationship with rope length, so it's clearly 1-to-1, and you have these data. Yeah, I would reverse the question. I would propose to explore the effect of twist, although the contribution from circular cross section is also, or the constraint on the circular cross section is also probably is more important, but it's very hard to tackle that. Yeah. So the data for twist 0 are available.
Any other questions for Renzo? Let's thank Renzo again.